So this work actually has appeared already. So what I'm going to show you is a joint work with Mirko. Mirko is now an assistant professor at Tor Vergata. Actually, I was at Rome before I came to Dortmund. And he was a PhD student of mine in postdoc for some time. And we worked on this topic. Let me explain you the problem. And so we can start from here. The problem is here. Maybe somebody else got through Zoom, but I'm not sure if the camera still shows me. But anyway, I mean, so this is a monthly number of burglaries in the south side of Chicago from 2010 to 2025. And there are 552 blocks. The data comes originally from this paper by Clark and Dixon. And these are just counts for all these 552 blocks. So at a specific time, this is just the block groups in South Chicago. So in each time, we have a 552-dimensional vector of counts. Okay? And this vector moves along time from 2010 to 2015. We want to somehow explain the evolution of this time series, but we want to take into account that there is a network, a known network in this case. And what is the known network in this case? That some of the counties are considered to be neighbors if they share a border, which is very reasonable. And if you have burglaries in one place, probably you have a similar number of burglaries in a very close place. So this is the main problem we want to consider. So the problem really is, can I describe the joint distribution of a 552-dimensional count vector? How can we do this? So we will try to understand, can we simulate at least such data? Can we simulate such data with this dimension? So the answer is yes. If you take a certain point of view, okay, and I will explain. Now, except that we want to have a joint distribution for a 552-dimensional vector of counts, we also want to be able to describe the autoregressive kind of process. So we need really to talk about multivariate count autoregressions first, to give foundations, and then to get into this network business. So let's see. Actually, there is a survey paper of mine, 2024. So first of all, what kind of multivariate count autoregressions exist? So the first attempt in this problem were these multivariate integer AR models. Okay, so YT is just like the number of counts, the number of a vector counting at each time t, the number of burglaries, the number of hospital admissions, or whatever. So people have written this kind of models. They are called this circle. It's a thinning operator. And they have done a lot of work. They have actually introduced this model, maybe in low dimensions, okay, but they introduced by Latour, also Frank and Brown, and then some properties of these models have been discussed by the Elliott community. So usually the estimation in these models is done by least squares estimator or maximum likelihood estimator, but they are computationally demanding. This is one class of models. The second class of models is the so-called parameter-driven models, what we call in time series like state space models, Kalman filtering and this kind of stuff. Okay? So this observed process is driven by an unobserved process. Actually, a very early contribution on this type of research is Jorgensen et al. 99 in Biomedical. where they develop a multivariate longitudinal count data. And Jung suggested a factor model for multivariate count time series. And more recent contributions include these references, especially West and Rand-Saiter. And there is also a review article that describes. This is not also my focus on this talk. My focus on this talk is the observation-driven models. I want to understand the observation-driven models. So we will develop a class of observation-driven models where they resemble the usual autoregressive kind of structure that we know. And we will study linear and log-linear models. Okay, we have proved that I'm not going to go into these technical issues. And the QML inference, we will see it later on this network. So let's see. So we have this 552-dimensional count vector. It's a dimensional count time series. And lambda is the corresponding n-dimensional, sorry, there is a tab, intensity process. Okay? So the question is, how can we describe the joint distribution of yt given the past? This is the same question as how can you develop a multivariate count distribution? I mean, okay? If you have continuous data, you can use a Gaussian, a T distribution. There are many established methods that we can use. And if we can describe the joint distribution of yt given the past, can we develop autoregressive models? And then can we do estimation? And how about prediction? This is the general things that we want to do when we deal with time series, okay? So that's the idea is, so we will start with a very simple model. It's a linear model. And previous results is hanging on Fico and Jung and Liu. So this is a multivariate linear model. So in each component, so you have the vector yt, and you assume that each component of the vector is like a Poisson, marginally Poisson, okay, with mean lambda it. And the whole vector lambda t, depends on some d plus a lambda t minus 1 plus b yt minus 1. So this is like a guards kind of structure. It's not really guards in this respect, okay? It is not, of course. So the mean depends on the past values of the mean and the past values of the ones. If the matrix A is 0, then you have just the usual autoregressive process of order 1. Of course, because this is Poisson, the vector lambda t consists of positive elements. So you need to make sure that D, A, and B are all matrices with no negative elements, otherwise it doesn't make sense. Otherwise. So marginally, we have a Poisson process with parameter lambda t, but we will show that their joint distribution is not multivariate Poisson. And how can this happen? How can we specify such a joint distribution? Actually, we can have any dependence between the I and J component of the Y vector. So how we should do this? So I will not give, okay. So usually people who are using this kind, I mean, they work on this multivariate count data, they use this multivariate Poisson distributions, there's a multivariate negative binomial, there are all these kinds of objects, but usually it's not easy, to deal with this, their functional forms. And also they always have like positive correlation among elements. So, I mean, of course, statisticians would like also to have some kind of negative correlation, models that can have negative correlation. So I will give you a construction by simulation, and I will explain step by step how to do it. So we have some in the model before, okay? We have some starting value n dimensional. We generate some a vector u from a copula. So we have marginally the uniform distribution. we introduce a transformation that you all know, which gives exponential with parameter, let's say, the ith component of this x vector is exponential with parameter lambda I. And then this is just a way to define a Poisson process with parameter lambda 0 for the whole vector, right? This is something that we do in the classes. So once we have lambda 0, we can get y0 once we have a starting value. Then we can use the model to get lambda 1, right? Because we know lambda 1 is d plus a lambda 0 plus b y0, right? So once we have lambda 1, then we can get y1 based on this. And so on. And so on. So you can simulate from this process. Okay? And you can do it even for n equal 550. You can do it. There are copulas. Okay? You can use this kind of thing. So this is a very simple idea. Now there is we just make sure that we use very simple properties of the Poisson process because we want to keep marginally the Poisson process, the Poisson property. Marginally, we have Poissons, but the joint distribution is something else. So you can actually simulate such networks as you will see. Now, let's understand a little bit better what is this doing. Before I go to these points, maybe I can give you a picture because the picture says everything, you know. So here is a joint probability mass function of a bivariate count distribution. So I use a Gaussian copula. This is for independent data, not time series, just for independent data. So I generate 10,000 independent observations, and I make like the histogram, right? The probability mass function. Okay, so these three plots, forget this plot for now. Okay. So I get a Gaussian copula, okay, and I consider the case of rho equals 0, independence, positive correlation, negative correlation. Plots, so the means, the marginals are Poisson with means 3 and 10. So you see, this is 3 and 10. This is where the marginals should be, right? The means. So this is just contour plots. Imagine like histogram, two-dimensional histogram, and you see where is most of the mass, the probability mass. Okay. So again, here you see positive correlation between the components, and the mean is 3 and 10, as it's supposed to be. And here is negative correlation. So we can simulate also negative correlation, 3 and 10. This is the, and this is it's okay, it's a negative multinomial. I mean, we don't need to worry about this. So we can actually have all kinds of correlations, right? So of course the Gaussian, I mean, the copula parameter will determine somehow the corresponding correlation in the data. But, you know, I don't think in the literature there are many PMFs that they can do this. Count distributions that they have negative correlation, for example. Positive, yes. So this is it's very easy to simulate it. So it's a construction by simulation. I don't have a joint PMF, you know, I mean, I just use simulation. So it's an easy conceptual construction. The multivariate Poisson distributions available in the literature are hard to work with. We keep the Poisson process property marginally. And the copula, this is another important thing, that the copula is imposed on continuous random variables, not on discrete, because there is a uniqueness problem with the discrete distributions. Okay, there is a uniqueness problem. And can be extended to other marginal count processes. You can have also negative binomial marginals, because you just need to do this mixed Poisson kind of stuff. So you can adjust your simulation method, and you can get negative binomials as marginals. So it's a way to do it, and it's for any dimension. So the models, you can write down the model, and I mean, if you have 2 dimensions, then the 2 equations become like this: the D's and the A's, and the D's are the elements of the D and the metric AB. So you can give some interpretation. If these 2 parameters are 0, then lambda 1 t depends only on its past value. If this is not true, then the parameters denote the linear dependence of lambda 1 t on lambda 2 and t minus 1 and y2 t minus 1 in the presence of the other, and similar results hold when the other alphas and b's are 0. So it can be interpreted, the model can be interpreted, you can give some interpretation. And similarly, we can define log linear models, which is, from my point of view, is a bit, they fit better current data. So marginally, you have Poisson, but again with the same construction. Now, instead of considering lambda, you consider log of lambda, component-wise. And you can get this kind of models. So a log linear model, now the modeling is done on the logarithmic scale. You don't need to worry about A and B being positive. Here, they need to be constrained, but they don't need to be positive. Parameters, as I said, allow to get negative values. We have, positive and negative correlation and covariates. This is the important thing. So you can easily include covariates. And the interpretation is the same as in the case of the linear model. So here, I just add 1 to make sure that this log is not 0. If y is 0, okay, so it's just a vector of 1s. So 0 plus 1, it's log 1, it's 0 again. Okay, so that's what happens here. So for all these things, we can do actually QML inference, and we have stability conditions, and actually people have improved the results. And also, you can get your estimators and so on. So let's go now to this network autoregression, because now we have the machinery to develop models for network autoregression. So what is a network? A network has n nodes. There is an adjacency matrix A, and in this case, the network is known, right? We know the dependency. We know the relations. It's a realistic assumption, like the counties example, like the burglaries example. Okay. And the elements of the A matrix is 1 if there is a connection between 1 I and j and 0 otherwise. And we can have also undirected graphs. As I said, A is in group of nanometrics. For example, social networks, space points transportation. YT is an n-dimensional time series. So you have a multivariate time series in a network structure. You can call this network time series. And we want to understand the network effect on the series over time. Of course, you can use vector autoregressive models, but we have a lot of parameters to estimate, and you can use one of your favorite penalization methods. So, Zhu et al. In 2017 suggested this network autoregression. So they said this is for continuous data. They said the ith component of the series depends on on the past value, of course, of t minus 1, and on the past values of the neighbors of I, plus some error. This is a very reasonable assumption, right? I mean, you say that you have a county, the number of counts, let's say at time t in this county depends on the neighbor, on a time t minus 1 itself, and on the neighborhood counties at time t minus 1, weighted. So the beta 1 parameter can be thought like a network effect. Is the average impact of nodes I connections. So the Wij is just the 1, 0 divided by n. And of course, the sum must be 1. And beta 2 can be thought as an autoregressive term, like the effect of autoregressive, excuse me, an autoregressive effect, the impact on past YIT minus 1. Okay? So this was for continuous variables, relies on IID assumptions, and the authors use OLS to fit this model. So this is kind of, this is like a way to reduce the dimensionality considerably by allowing this kind of representation. It's like another way to do this thing, okay? So you say like there are these parameters, beta 1, beta 2, and this beta 1 and beta 2 somehow have an impact on this network. If it is some kind of stable process, you expect that you have something. So now we can think about the multivariate count time series with a mean lambda t. So the Poisson network autoregression is the same idea. So we have this YIT given the past is Poisson, but again, this is marginally. This is marginal. The joint will be, I will explain the joint in a minute. Where lambda IT depends on its past, on its neighbor, the neighbor of I weights, the values of yj t minus 1, and that yi t minus 1. In this case, we can have a stochastic representation with martingale different sequence. It's okay. So we can write the whole thing yt as nt lambda t, where nt is a sequence of n-variate popular Poisson process, as the one I described before. So you can do this. And then once you put all these lambda t into a vector, you stack all these lambdas, then you can write this form like a multivariate autoregression, where G is this matrix. This is with the Wij. It carries the network information. It's this diagonal times plus the identity. So you can just write it down. So you have like a linear model, right? It's a linear model. And more generally, you can think about P-order autoregressive model. So you have this lambda IT, and then you see now you have all these beta 1 H. H goes from 1 to P. These are the P back neighbors, P back values of Yj, of the neighbors of I, and all the P values back of the ith value, of the ith observation at time. So again, you can, of course, if p equal 1, then you can put these coefficients to obtain 3. Just a simple extension. And then you can write also this yt is just a coupler, okay? And then you can you have an autoregressive model of order p, where these matrices are given by this expression. So if the sum of these coefficients actually is less than 1, then this process is stationary and ergodic and has moments, even when n goes to infinity. And so there are very similar conditions to multivariate ARMA models, and do not depend on the copula, right? Because there is a copula here in the construction, but they don't depend on the copula. Because you have actually assumed that the marginals are Poisson. This is the important thing, that the marginals are Poisson. More generally, you can think about nonlinear Poisson network autoregression. We also have done work on log linear. So now lambda t is a nonlinear function. I will give some examples in a while. And again, the same notation. Theta 1, so this function depends on a parameter vector theta, where theta depends, can be decomposed further on 2 parameters, theta 1 and theta 2. Theta 1 is like a vector of linear model parameters, I will explain why. And theta 2 is another vector of nonlinear parameters. Okay, there are many. Why should we consider nonlinear models? Okay, we know already from univariate time series that nonlinear time series models are more interesting, right? And they can describe more complicated structures. And definitely in this social network analysis, you have these superstars with huge number of followers, and they have an exponentially large impact with respect to the standard user, right? So there are many. Why should we consider this kind of models? Here are some examples of nonlinear models. So suppose for ease of notation, let's put xit minus 1, the average, the impact, let's say, of the j of the neighbors of I, the weighted sum of the values at t minus 1 of the j, where j is a neighborhood of I. So here's one model. I mean, of course, this is not just a model, right? So we call this intercept drift. And if gamma here, you see this is the nonlinear parameter gamma. If gamma is 0, then you have linearity. So it's like a deviation from linearity. You can have this kind of models. This Teras Virta has done a lot of work on this kind of stuff. Here, if alpha equals 0, then you have again a linear model. Okay, and then threshold models. So you can think about threshold models, right? And if these parameters are equal to 0, then we have a linear model. And you can write more things, of this. But let's think about this. So the smooth transition model is a model that actually tells us we go from one regime to another regime smoothly. But the threshold model, you can think about going from one regime to another regime, but abruptly, very fast. Okay, it's this is smooth, and this is threshold. Okay, it's continuous. So there are stability conditions also for this. If we assume this kind of contraction, then we have all kinds of results. And for the special case of these models, you have this kind of conditions. But anyway. So you can also think about log linear models. It's the same idea. Instead of using lambda IT, you just use log of lambda IT. And then you write down in terms of the neighbor values of new IT and the past values of YIT. Of course, here we can put covariates, and we have analogous results also here. So how should we do inference? How should we do inference? So we take a quasi log likelihood. So this is not the true log likelihood. This is just a log likelihood based on the assumption of independence among series. And the copular structure is not included here. So you can just write the score and the Hessian, and then you can assume that some matrices exist. It's not, of course, everything depends on the structure of the network, right? I mean, otherwise these things will not exist. And we can have like a central limit theorem and storm consistency. Of course, the results hold for all models, I told you. But the assumptions depend on network structure. Otherwise, it's impossible. And it's very strange assumptions, okay? But that's what it is. And the assumption guarantee existence of Hessian and information matrices. Okay? So there are these kind of things. So the next thing that I would like to discuss is, can we test for linearity? Can we test for linearity? There are many ways, there are many reasons why we want to test for linearity, for evidence, for model selection. for consistent inference, because nonlinear models, nesting the linear models suffer from identifiability issues. Also from practical usefulness. And we want also to do some general inspection of the data. So let's see how we can test here for linearity. So as I said, the parameters in the previous model, we have decomposed it like into two parts. Maybe I'll just go back. So for example, here, theta2 is gamma. Here, theta2 is alpha. And here, theta2 is like A0, A1, and A2. Theta1, if you remember, is a vector which consists of linear model parameters. Theta2 are the non-linear model parameters. So suppose we want to test this component-wise, and then if theta2 equals some specific value, usually 0, then we have the linear model. So we'll, because everything has been based on the quasi likelihood, we have a quasi score. We will use a score test, and actually it's much better to use the score test because it's computed under the null. Okay, so it's a bit better. But there are problems now. For example, there are cases where the parameter is identifiable, and there are cases where the parameter is not identifiable under the null hypothesis. For example, again, I'm sorry to go back. Here, if gamma equals 0, then this is okay. But if here alpha equals 0, this gamma parameter is not identified, right? And here, if these three parameters are 0, the threshold parameter is not identified, right? So it's a problem. And this is a standard problem. If we have identifiable parameters, then this score statistic that I show you goes to chi-square with k degrees of freedom. K is the dimension of theta that we test. If there are non-identifiable parameters, then the score and the test depend on this gamma, like this gamma that I saw over the threshold. So the standard theory is not applicable. So we can actually prove that this score and this Lagrange multiplier test converges to this, which is a chi-square process. And this asymptotic distribution cannot be tabulated. So we need to do something. So there are, to get the p-values, the one is bound for p-values. This is the old suggestion by Daly. So there is this formula. It's a handy formula. N is the maximum of the test statistic, and it's over a grid of values. And V is the total variation. It's very simple and fast, but it's only bound. So we have a conservative test. It's only for scalar gamma. So again, and it requires differentiability, so it cannot be used at threshold level. We can think also about bootstrapping, on stochastic limitations, or wide bootstrap nowadays. So you can generate normal 0-1 data, and then you just take the score and you multiply the score times this normal one. And you can you can form the Lagrange multiplier test, you take the string, and you can compute the p-value based on this. It's of course time consuming when the dimension is large, but this is what you can do. So let's see. Again, the monthly number of burglaries. And now we can fit it. We can fit the model. And we have fitted a series of models, a linear Poisson network autoregressive model of order 1, a log linear of order 1, a linear of order 2, and so on. And we have used this information criteria. The AIC and the BIC, if you feel that the Poisson likelihood is correct, it's okay. Otherwise, you can use this. It doesn't matter which criteria makes you happy. The thing is that, well, actually, for this problem, this is better. This is better. Okay? Scientifically more sound because it will be based on quasi information. Okay? So this model is, looks okay. And we see the estimators are positive, right? So there is a positive effect on the number of burglaries in the surrounding counties at time t-1 and time t-2. And there is also a positive effect of the number of burglaries at the same time, the same county in times t-1 and times t-2. Okay, so everything is positive. And check also the log linear model. Okay, this we don't care, but this also the corresponding coefficients are all positive. So it seems there is some positive effect. We also tested for linearity. So maybe there is a nonlinear. So this is the only thing that we find significant, let's say. The bootstrap, we bootstrap based on chi-square, the Davis bound, and the bootstrap approximation. So it seems that actually we have a model which there is a nonlinear shift in intercept, but there is no regime switch in these models. Okay. So I think we have introduced useful models allowing to measure the impact of networks on multivariate time series of counts. Of course, we have some theory and QMLE, and there is a problem of unknown network. This is when the W is stochastic in matrix, over dispersion, heavy tails, zero inflation, time varying networks. Some people now are working on other topics like group networks and so on. And this work has appeared in Journal of Time Series, in the Annals, and we have a package that can fit these models. It's called PNR, and it has appeared in our journal. So I think that's it. That's what I have to say. Many thanks for your invitation. I will be happy to discuss with some of you. And I'm really happy to be here again with friends. Thank you so much.